All right, we are back. We are gonna be solving the daily. Here's the link in chat. So the problem is called longest string chain. So we're given an array of words where each word consists of a lowercase English letter, of lowercase English letters, and word A, words of A, is a predecessor of word B if and only if we can insert exactly one letter anywhere on word sub A without changing the order of the other characters to make it equal to word B. For example, here we have ABC, which is a predecessor of ABAC because we have inserted an A here between the B and the C, while CBA is not a predecessor of BCAD, and that is because we changed the order. So we inserted a D, but the order of B and C is reversed, is inversed. And then it defines what a word chain is. It's a sequence of words 1, 2, up to K here, which is not empty, where, yes, each consecutive pair of words, so word 1 is a predecessor of word 2, word 2 is a predecessor of word 3, and so on. A single word is trivially a word change of size 1. Return the length of the longest possible word chain with words chosen from the given list of words. And we get 2 examples, 3 examples, A, B, BA, and so on. And they're up to 1,000 words. And each word is of length up to 16. And like they said, they only consist of lowercase English letters. All right, so okay, so here the first observation is that we can translate this into a graph. So this vocabulary of predecessor and successor, which is not used here, but if A is a predecessor of B, in this case you can call B the successor of A. And also this idea of chain, a chain, is also similar to a path in a graph. So here we could interpret words as nodes in a graph, and this relationship between pairs of words, the predecessor, is an edge, a directed edge. So in this case, from A to B. And then, like I said, a chain is a path, is a sequence of words and we're asked then to find the longest possible path. The length of the longest possible path in this new vocabulary, in the graph theory interpretation. So you might notice that this is a very famous problem. So the longest path problem on a graph. So when I mention that a problem is famous or fundamental, my point usually is that the problem is very general. in this case at least, and it's worth knowing because it might come up. So yeah, given that it's very general, very abstract, how did you know it was a graph? Well, so welcome, Wolfgang. So the hint that I mentioned is that these words, the predecessor word, is a word that is used in graphs. And also the word chain, which is a sequence of the words, it's also analogous to paths. So that was the hint. In general, whenever you have objects that are related in pairs, that can be interpreted as a graph, because that's what a graph is. You have nodes. We call these objects nodes, and the relationship between pairs we call edges. So it's useful to notice that relationship, because once you made that translation, you can use all the knowledge that you have. You can import the knowledge from graph theory that you already have, like traversing algorithms like BFS, DFS, shortest paths, whether it's weighted or not, etc. Once you make that connection, you can use all that knowledge for free. And in this case, we identify this problem as the longest path problem. And this is like I said, this is a very famous problem. Thanks. Yeah, no problem. That's why we are here. So the longest path problem. So I'm gonna share this in case you have time and you're curious. But one thing to note is that there is no solution to this problem in general. There is no... Oh, thanks for the follow, Wolf. Thank you, Jesse. So one thing that you can know is that there is no polynomial solution to the general problem, to the longest path, finding the longest path on or the longest path length, in this case, of a general graph. And here the size of the graph is it's not small, it's not a tiny graph. So that suggests that this is probably not a general graph, because otherwise we could not solve it. And indeed, if you think about it, so because of the rule for predecessors, we always go from a word of size of length L to a word of one more character. Exactly. That's how this is defined. So that means that you can't have edges that go back or cycles. So one way to think about it is you could write down the graph organized by the length of the words that the nodes correspond to. So for example, if you have a word of length 1, you'll put a node here, another node here, maybe you have 2 of them, and then length 2, 3, 4, and so on. And notice that all the edges are directed and have to go from one level to the next, right? notice that you could have things like this, but they all have to go from one to the next. Maybe you have a word of length 4, but maybe it is not connected, but it is connected to a word of length 5, and so on. So all the edges in this diagram go from left to right. You cannot have an edge that goes from a node to itself, because that would be a successor that has the same length. We said that that's not the definition. And we cannot keep levels, and we obviously cannot go back. So that means that the graph is acyclic. It doesn't have cycles, and since this has arrows, it is directed. So this is what's called a DAG, which is just a fancy name for what we said, directed. A directed graph that doesn't have cycles. Directed acyclic graph. Okay, so, and we are in luck because it turns out that the longest path problem turns out to be easy for this kind of graph, for a DAG. That is because we can solve it recursively. If we know the longest, if we want to know the longest path, so this will give us the length actually, but let's call it like this, from node U, then we can check the maximum of the longest path from U, where from B, where B is are all the successors of U. Okay, this is kind of a pseudo code notation, but we need to add the current node, so this is 1. And if it doesn't have any successor, then the length from U is going to be 1, but we're not going to write that down. It doesn't matter. But the point is that we can have this recursion, and since there are no cycles, we are eventually going to get to a base case, which is the one that I mentioned, where a node doesn't have any successors anymore, and we can use memoization to compute this quickly without recomputing the longest path for each node. So there are n nodes, so that's how we define the size of how we denote the size of the graph. So there are going to be n subproblems here, and so if we use memoization, we're going to solve n subproblems. So now that we know how to solve that, we still need to know how to construct the graph, because we're not given the graph. We're explain how the nodes connect, but we are not given the connections directly. And here there is one little observation that you can make to speed up your algorithm, which is that so there is a difference between, if you want to compute to find the potential successors for a word, well, you would have to try out So there are different ways to figure out what the edges are. So the most brute force way would be to just consider all the pairs of words and check if one is a predecessor of the other, which would be easy. But the problem is that that's going to require going over all the pairs, which is quadratic. So the size here is 1000. So it seems that that could work. But yeah, so I don't know why. This is a medium problem. I would expect that solution to not work for a medium, but in any case, it's not hard to realize that instead of going over all the pairs, you can try to use these definitions and to use the fact that the alphabet only has 26 letters, sorry, and the words are short, have only 16. Then, for example, if you want to know all the potential successors of a word, you can try inserting a character on every position, right? So there are, if there are k letters, there are k plus 1 insertion points, and you have 26 possible characters on each. So that is around, so 16 times 26 is smaller than going over all the 1000 words. Hey, what's up, Adnan? So we're trying to solve the daily challenge. Hey, thanks for the follow. So that means, and once you have a potential successor, you can check whether it is effectively in the set of words by storing the words in a set data structure, so that we can check easily if it's contained quickly. But notice that it's even better to do it the other way around, because if we want to know so we try to find all the potential successors for a word, but what if we try to find all the potential predecessors of a word? Then they're even less than that, because for each letter we have the option of removing that, and that is going to give us, so it doesn't depend on the size of the alphabet, just on the length of the word, which we can assume is constant, and it's pretty small, that 16 in this problem. So that gives us a way of finding all the edges on our graph. So we're going to create a one before we start coding, one thing that I did not explain was that, why is this a DAG and not a tree, right? Because so a graph without cycles can be a tree, except when it has these kinds of edges, right, that go to the same node. And that could happen because if you have, for example, the word cat and the word car, they could both have the word cat as a successor, right? Because here you're inserting a T to the end, and here you're inserting an R to between the A and the T. And this doesn't have the structure of a tree, because this node card has 2 predecessors and a tree has only 1. Each node should have only 1 predecessor. So that's why this is a DAG and not a tree. but for our purposes, it doesn't matter. We can still solve this problem quickly. So we are going to create an adjacency list of this graph. That's the representation that is. Yes, eventually we're going to use DFS to do the memoization that I said. But it's important to save the to save the values so that we don't compute them more than once, or marking, in some sense, marking them as visited. But first, let's construct the adjacency list that is going to allow us to do the traversal. So let's use the words directly. So for a word in words, initially we'll have an empty list of adjacent nodes, and then for every word in word, we are going to consider removing every character in word, so that the predecessor is going to be the word up to the I element, but without the I element. So that is a potential predecessor, but for it to be an effective predecessor, it has to be in the adjacency list. So this is we created a dictionary, so it's fast, it's quick to check. It's a constant time to check whether it is a node in the graph. And in that case, we're going to add so the predecessor goes to the word, right? So now we have created the adjacency list representation of the graph. We have constructed the graph, and let's use a helper function so that we decompose the problem clearly in the code. So the longest path of the adjacency of the graph so no, I don't think we'll need this. So yes, let's do memoization. So longest of the node u, it's going to be the maximum. This is exactly what we wrote here, right? It's going to be the maximum for all the adjacency nodes in u, and we call recursively, and we add 1 because we need to add node u, and there is the possibility that u doesn't have any successor, and in that case we default to 1. We only count u. So I guess a different way to do this would be to add the 1 here, because we always want to count u. And so, but now we need to start from any potential node, right? The path could start from anywhere. So let's do also an iteration from, let's find the longest starting from every node. And yes, like you said, this is a hash map. Yes, so this is a dictionary in Python, which is essentially a hash map. It's a hash table internally. And so yes, essentially this is DFS. Now I focused on LeetCode as my name suggests. But I keep it mixed. I sometimes do medium, sometimes I do easies, and sometimes hards. So yes, my point now was that this is essentially a DFS because we are doing a recursion, and since we are caching, this saves the results of the calls so that we don't compute them more than once, and that is essentially a way of marking the nodes of DFS, depth first traversal. So yes, this is essentially a DFS, as you said. So let's see if it works. So it passes the examples. Is there any edge case that we can think of? All right. So that's cool. And it's fast, relatively fast compared to other Python 3 solutions. So yeah, I think that's all. Let me do a recap. So this is why I titled this stream longest path. This is the longest path problem. We mentioned that in general, this is what is called an NP hard or NP complete problem, which means that there is no polynomial solution to it, or at least it's strongly suspected that there is no polynomial solution to this problem. But we realized that this was not a general graph. This was a DAG, and we explained why. Because all the edges go to one side. There are no back edges, so there can be a cycle, and that's what a DAG means, and a cyclic. And then that means that we could solve it by dynamic programming, but memoization, by defining this recurrence relation. And yes, and then we thought about how to construct the graph, which turns out that if we do it this way, we don't have to do a quadratic algorithm. We can essentially do a linear in the number of words. So that I think that's why this is faster than most solutions, probably. I think this could pass with doing all pairs. So yeah, that's all I have for now. Thanks for watching. I hope you learned some general ideas based on this particular problem, and thank you for your support. Bye bye.